And they might feel very comfortable that they're working on the right thing, but they do need a level of nuance around what to work on first, what to expect when, what is R&D versus what is rollout.
What the staircase really clearly shows, again, for transport, as I said earlier, 80% of the emissions on rows A to C. So what we have in transport is a big problem that's relatively straightforward to solve, and then at the top, a small problem that's very difficult to solve. Well, which of those two things should you focus on as a policymaker? Clearly, doing the stuff that's the bulk of the emissions and that you can accelerate today.
Hello, I'm Michael Liebreich, and this is Cleaning Up. Our episode today is about electrification and the Electrification Staircase, which is a tool developed by a number of co-authors who are joining me here today in Brussels for a discussion about the staircase with its originator also, Adrian Heel, who is the Director General of the Electrification Alliance. So our co-authors next to me, I was one of the authors, but the co-authors, we have Tom Butler, who's an associate with the Regulatory Assistance Project. We have Will Drake, who is an associate with Liebreich Associates, I've heard of them, and Ecopragma Capital, and Dr. Sylvia Madedu, who is a solutions architect with Schneider Electric, who are, of course, one of our Leadership Circle members, formerly with the Potsdam Institute, where she was senior scientist, and the author of a paper which I read, and I brought her onto Cleaning Up for episode 103 in October 2022, which opened my eyes to just how important electrification would be, particularly in industry. So a highly qualified panel. And let me just say, to get us going, electrification, I have been doing this for over 20 years now, and I've been reading scenarios in IPCC reports for longer than that. And there is no scenario for any sort of transition, any sort of cleaner energy system, which does not go through electrification. Electrification accounts now for around 30% of all use of energy. All the scenarios, every single scenario for the future that looks at a cleaner energy system has electrification growing to 60, 70, 80% or more. And yet we don't make rapid progress. And one of the reasons we don't make progress lies in a problem that we all have today, which is narratives and the narrative wars and the culture wars. So we hear about heat pumps that don't work. We hear about electric vehicles that don't work. We hear that electrification can't work for high temperature heat and so on. And then we hear a narrative that there is another solution that will work that's much better, and it's called hydrogen. And you will also know that I've spent quite a few years trying to debunk that narrative and explain what role hydrogen might and probably might not have in the future energy system. And I used in that conversation something that was called the hydrogen ladder, and many of the audience, possibly the majority, possibly close to all, will have heard of it. And it did a magnificent job of resorting the narratives, the discussions, and focusing people on what would work and what wouldn't. And so I joked with a friend of mine, Adrian Heel, that we ought to do a similar thing for electrification. So Adrian, kick us off. Tell us, what is the Electrification Alliance? And then what is the role that you see for the electrification staircase?
I mean, to be clear, there's still very much a role for the hydrogen ladder, because those stories and narratives are still out there and still need to be continually debunked, which is a great frustration. But the Electrification Alliance, very simply, is the organizations in Europe that generate our electricity, that distribute it with the wires or smart demand, the smartest end uses, most efficient uses of that electricity, and the people who sell it as well. So it's that whole supply chain of electrification in Europe, and that's who I represent here in Brussels to the institutions, the European institutions that are here.
Now, I've rather foolishly omitted to mention, for the purpose of the video, the YouTube and the podcast audience, that we're recording here in Brussels in front of a live audience. So the first they will have known about that is perhaps have heard the laughter at my mistake there, calling the Electrification Staircase a hydrogen ladder. But we are here in front of a live audience, and those who are watching on YouTube and the live audience can see behind you the Electrification Staircase. So we'll be referring to that as I bring in the different co-authors. So what are the rows? Can you do this without looking at it? You do need a crib.
Well, there's 6 rows, right? And it runs from what's electrifying now to what's going to electrify maybe in the 2040s and more speculative uses. So the stuff in the first 3 rows especially is the absolute no-brainer stuff that is electrifying now and either everywhere in the world or at least in substantial pockets of the world. And so that's things like home heating, it's things like breweries, it's things like textiles, it's low temperature process heat in general, as well as road transport, as well as buildings. That's the stuff that's electrifying now. And the focus really has to be on getting that stuff going as fast as possible.
Okay, so you have row A, which is commercial now in most places. This is essentially no-brainers, and it should be going at absolute full speed. You've got row B, which is commercial now in many places, but perhaps not universally, and row C, which is commercial now in some places. So some places it actually shouldn't even need a regulatory response, but in other places it might. And that's rows A, B, and C. And then take us through, you've got D, E, F, and those are?
So D, E, and F is where we're getting a bit more into the, not speculative, it's just we're not quite there yet in terms of mass commercialization. So we've got river transport in there, you've got higher temperature industrial processes that need to be in there. Those are, generally speaking, more energy intensive industries, so they don't have the flex or the efficiency of heat pumps. But those are the things that we need to start preparing for now because they're a larger industrial shift.
We can already see that one of the things we're trying to do here is separate out use cases, so people can't just say electrification doesn't work because you will never have a transatlantic ship that is electrified, or you can't do long haul aviation and therefore it's all, you know, those people who say electrify everything are fools. And of course that's gaslighting, because we're not saying electrify everything, we're saying look at the staircase. So Tom Butler, with Regulatory Assistance Project, you worked on the staircase, and it should be said that all the authors worked across everything, but you have particular expertise on in the area of the heat. I wanted you to talk us through the ABC rows of heat and industry.
So firstly, let's think about what actually makes something obvious, what makes it competitive. What kind of factors make something land in this ABC zone? So we're thinking about things like, are the technologies mature? Are they ready? We're thinking about, are they cost competitive? Do they bring code benefits? Are they easy to implement? There's all these kind of factors that we're considering. If we start with comfort heating, space heating, so really what we're talking about here is heating buildings with people in them. If we start on this row A, so we're looking at new single family homes and multi-family homes. These are some of the best opportunities for electrified heater technology. Particularly, we're talking heat pumps here. So heat pumps, they're definitely going to be the dominant technology for space heating. Why is that? What makes them so great? Well, heat pumps are ultra efficient. They're not generating heat like all the kind of old school heating technologies that I have. They're pumping heat, they're moving it. And with that, they can bring a massive efficiency advantage. With that efficiency, you're going to get cost savings. So we've never been able to heat our homes so efficiently before. And heat pumps are really going to drive those cost savings. Maybe I should differentiate between row A and row B.
I was just going to ask because it's so obvious when you have a new build. I just look at anything that is being built today in a colder climate and it doesn't have a heat pump from day one when you're building it. It is completely absurd. It is a failure of imagination. It's a failure of finance. It's a failure of regulation. Row A, and it's not just heat pumps, and you've got some other things on there, but that one's, in a sense, that should be so obvious. But then you've got row B and row C, which are not quite as obvious. Sometimes they work, sometimes they don't.
So maybe we just focus quickly on what does a new build mean? So new build, brand new buildings, these are buildings with much better modern fabrication standards. So if you fabricate a building with modern materials, it can be efficient, it can retain its heat better, and that means that you can have a smaller heating system, a more efficient heating system, and that's really reducing the cost of actually operating a heat pump anyway. You can also design the heating system from the start to be tailored to that electric heating system. So, you don't need to do any kind of redesign, you just get it right from the start. You can also finance the actual equipment as part of the building, so you can lump it into the mortgage. Obviously, if you have lower bills, then that's preferential to lenders. So that's what's making new builds super easy. If we look at retrofitting existing buildings, there are some slight complications which make it not quite as easy as a new build. There may be some requirements to upgrade your emitters. So those are your things like your radiators, the things that actually expel the heat into the house. You may want to do some fabric improvements as well. I mean, it's worth saying that heat pumps can heat houses without those. It's just that if you put in those improvements, you're going to have lower operating costs.
And with the retrofits, presumably you're seeing costs coming down, but also there's a sort of natural asset replacement cycle. So if you try and do a retrofit at the wrong time, you've got a relatively new boiler, you don't do a retrofit. But so there's a time element here. And, I think I should say that the reason it's a staircase, not a ladder, was where the hydrogen ladder was just it was essentially the vertical scale is probability. This will work, this won't work, and some stuff in between. Here you've got a bit of nuance around time. So retrofits still work, but you probably want to do the heat pump or the electrification of heating when you're doing a renovation anyway. So that's the time element. I want to just pull in also, there's some other, and you work quite closely with Sylvia on some of the industrial processes, because when you get to see the things that are perhaps patchily working now, but you can expect to grow over time, you're getting things like paint lines, paper drying machines. Those are still probably heat pumps, but you also got things like glass melting, ceramic kilns, which are higher temperature, but they're working now commercially in certain parts of the world or in certain configurations. Do you want to talk about those briefly?
As we said, when we're thinking about whether something's obvious, we're thinking about whether it's cost competitive, whether it's technically mature. Now, from a technical perspective, let's take glass furnaces, for example. So electric glass furnaces have been in operation for a long time and they are widely deployed. Historically, they've been for niche products, very high-end products, things like high-end spirit bottles, alcohol bottles, very clear, perfect products. The relative cost of electricity to gas has meant that historically people have favored gas, but now as people are looking more towards electricity, we're realizing that electric glass furnaces can bring huge efficiency gains. Historically we think of heat pumps as the really efficient technology, but what we forget is that electric heating can be very precise, it can be very targeted, and that means that even if you don't have the efficiency of a heat pump, say where you're getting 4 units of heat from 1 unit of electricity, even if you've got that 1-to-1, if you can target the material that you want to heat more efficiently, which you can with a glass furnace, then you can potentially get a reduction of 50%, so you're halving your energy use relative to the counterfactual.
I think that's such an important point, and it's also a point where there's relatively poor data out there, because the example I give is if you use if you boil a gas, or you boil a kettle on a gas hob and you've got efficiency of 30-40%, most of the heat goes around the kettle, goes up gets vented out in your flue, but if you then go to an electric kettle, you might get to 80%. But But if you put 1 cup of water into a microwave, you'll get 95% efficiency. So it's not like for like. When you electrify these processes, because it's so much, as you say, more precise, the heating is more precise. And there's other factors like it's a more pleasant factory to work in. You don't have the same churn of the workforce. You don't create pollution in the neighborhood and so on. So there's a lot more to this than just, efficiency. I think we're going to come back to some of those when we talk about some of the other industrial processes, the ones that might be a little more speculative, rows D, E, and potentially F. Pull out one more favorite from row C, one more industrial process, just to give some idea of the stuff that really is happening pretty much now, maybe not everywhere, but in industry.
Let's take steel, for example. So historically, you've had big integrated steel sites where you've got lots of big industrial units all linked together, passing gases around, big, dirty, lots of combustion going on. What we're seeing now is that the downstream processes in a steel plant, so this is kind of reheating and forming the blocks and shaping the products, these can all be electrified. And we're looking at things like induction heating, resistance heating. And this is really, it's rapid, it's efficient, it improves the productivity. And like you say, it improves the environment for workers. You don't have this image anymore of people with big heat shields on, sweating, laboring away. It's a much more pleasant and contained environment. So that's something that's very promising, and it's being deployed right now.
Okay, thank you. Now let's move on to transport. Will, you've got a pretty long history, 4 or 5 years of transport. And I should also note that Will has been working not just with Liebreich Associates, helping me with all the work that I do on cleaning up and other sort of media engagements, but also via EcoPragma Capital on Pragma Charge, which is the electric truck charging business that we're building pan-Europe, across Europe. So Will's been absolutely in the bowels of freight electrification. I can testify to about the last 2 years of that, but he's got a few years before then. So talk about the transport electrification, particularly focusing on the ABC rows.
Yeah, certainly. And I like to focus on the ABC rows because remarkably, those 3 rows alone are almost 80% of transport emissions. And in fact, 50% of transport emissions are just on row A. So how have we got there? Well, this is actually really a tale of 2 things that have got us to a point where so much of transport is sitting on rows A, B, and C of the ladder. The first is batteries. Over the past 15 years, we've seen a 93% drop in battery prices, a doubling in energy density, a doubling in lifetime. And what that's done is really push things down to the bottom of the ladder. 8 years ago, when I was still a student, you couldn't even buy an electric truck. That was it. Now, if you want a long-haul truck, you can buy one. If you want a regional truck, you can buy one. If you want an urban distribution truck, you can buy one. Every single manufacturer, all of them are very focused on this. The other important point, though, is that those bottom 3 rows of the ladder for electrification of transport were never as difficult as they were made out to be. Because previously, people were looking at stereotypes, not data. I've worked a lot on trucking. When people think of long-haul trucking, they think of 2 people getting in a cab, driving non-stop from Rotterdam to Slovenia. 16 hours non-stop, one chap is sleeping while the other one's driving, and then they swap over. That stereotype is 0.2% of heavy-duty trucking. 0.2%. What heavy-duty trucking is really about is it's driving from Valencia to Madrid, or London to Birmingham, or even London to London, doing last mile distribution. And what that means is that almost all of the journeys that the trucks actually do, we can do with electric trucks that are available today. And in some cases, we can do them cheaper than diesel with electric trucks available today. I think the other important point to make here is that this staircase is very dynamic. What's commercial in some places today, next year will be commercial in more places. One of the key points to make here is that whilst we've seen a truly transformational change in batteries over the past 15 years that's unlocked all these sectors in transport at the bottom of the ladder, even relatively small improvements can have a huge impact. For example, if my truck increases by range from 300 to 400 kilometers, that may not sound like a lot. But actually, what that allows me to do, just that small improvement in truck performance, allows me to drive for a full 4.5 hours, which is the maximum a driver can legally drive before taking a mandatory break. So we've seen rapidly improving technology and disproportionate benefits from incremental improvements in technology, which mean that most of road transport is sitting near the bottom of this staircase, and the roads on the bottom are getting bigger and bigger year by year.
An example of that marginal improvement, which makes a big difference, I'm just thinking from Pragmacharge, is actually Valencia-Madrid.
Yes. Valencia-Madrid is actually between 300 and 400 kilometers distance. And so this improvement we've seen in the past year or two with the availability of trucks that can now drive 400 kilometers in all weathers instead of 300 kilometers has opened up this key trucking route, which is Europe's 6th busiest route.
And without having to do a top-up, I want to just draw attention to trains, because I know that we've had you chained to the radiator working on trucking for the last couple of years, but there are trains on here as well. And that's a really interesting one, because that was one where I was told endlessly that the solution for trains is hydrogen, because we have diesel trains and the solution therefore must be hydrogen. And certainly, I've been watching that in disbelief when you see India, 99% of their wide gauge railway is now electrified. But you've got trains in a few different places here, mainline trains, branch line trains, and then there'll be sort of remote trains. What is happening on rail?
Yeah, so I think trains are a good example of how previously people always used to say it's big or it's heavy, therefore it can't be electrified. But actually, we can talk about mining equipment, we can talk about trucks, we can talk about ferries, we can talk about branch line trains. Those are all things that are very energy intensive, and so because they're big, the economics can actually be very favorable. Because you have very large operational cost savings from all the fuel that you're saving. I mean, trains, obviously, long distance mainline trains we've seen electrified for a very long time. But in the UK recently, we've seen remarkable developments in branch line trains. The Great Western Railway in the UK is now operating electric branch line trains, and they're actually a perfect use case for electrification that was hiding in plain sight. They're simply shuttling A to B all day. So you can optimize your system perfectly. You can right-size your charging infrastructure.
You can also do battery on a train. For those, there are places where it's hard to electrify everything because you've got tunnels or you've got junctions or you've got urban sections and so on.
Yes, and so these GWR branch line train, I should say, they are battery electric trains. They charge at the start of the journey, do the journey out and back, and then they charge again. And of course, because you're on a railway, weight doesn't matter. So you can have the heaviest battery that you need.
And one of the secret weapons is, of course, even if you're going uphill and it's very energy intensive, you get that energy back, which you don't when you've burnt diesel.
My favorite example is the Australian gravity train, which I'm a physicist. Perpetual motion doesn't exist, but it gets pretty close to perpetual motion, because what it does is it's a train that loads up in the mines in Australia, drives downhill to the port full, charges the batteries with regen braking, unloads, and then drives back up empty. And there was no charging needed in that whole trip.
I'm hoping to see the first Pragma charge routes where you go up from a port, take, I don't know, paper in Finland, it might be an idea,
Yes.
and then it comes down and it's the weight of the paper that actually charges the truck. We'll see if we can get that one going as well. Perpetual motion, not. Cleaning Up is proud to be supported by its leadership circle. The members are Actis, Alcazar Energy, Arup, Copenhagen Infrastructure Partners, Signum Capital, Davidson Kempner, EcoPragma Capital, EDP, Euroelectric, the Gilardini Foundation, KKR, Mitsubishi Heavy Industries, National Grid, Octopus Energy, Quadrature Climate Foundation, Schneider Electric, SDCL, and Wärtsilä. For more information on the Leadership Circle, please visit cleaningup.live. To keep up with all that's going on in the Cleaning Up universe, make sure you subscribe to our newsletter. Written and edited by my long-time New Energy Finance and Bloomberg NEF colleague, Angus McCrone, it comes out every second Monday. Angus provides the latest on the episodes we're recording, the events we're hosting, stories we're watching, and what Bryony Worthington and I are up to. To sign up for the Cleaning Up newsletter, visit cleaningup.live. I want to move to Sylvia and talk about some of the more difficult heat and industry use cases. But Sylvia, this is all your fault, right?
Yes, thank you, Michael. I guess so. Some years ago, I co-authored a paper on industry electrification, estimating the potential to electrify the European industry. And I think that this study was pretty groundbreaking and probably represent, I don't want to sound too cocky here, but it was a milestone in the sense that we looked at technical potential. So we looked at what can we electrify with the technologies that we have today. And we wanted to debunk maybe something that you will still read today, 5 years later, 6 years later, which is that the heavy industries cannot be electrified, or industry cannot be electrified due to the lack of technologies that reach high temperatures that are needed for industrial processing. So we looked at these technologies and we actually found out that we have plasma torches that reach 10,000 degrees. We have induction furnaces that reach 3,000 degrees. We have resistant furnaces that reach above 1,000 degrees. So in reality, what we found out is that temperature is not the issue if we want to electrify industry. So what are the challenges? There are, of course, other challenges. These are both economical challenges and also technical challenges.
I asked Sylvia to mention some of the heating technologies because I have been told countless times that electrification doesn't work at high temperature. And my response to people usually has just been arc welding. And that sort of takes the smile off their face. And then you've given us a list of other ways of getting to high temperatures using electricity. But if you could now map that onto a couple of use cases, perhaps chosen from the DEF rows. These tend to be things, Tom's talked us through some of the industrial uses that are happening now, maybe not everywhere. But you've got some there that are going to take a bit longer, but you are seeing pilots and you are seeing, so we've got the likely commercialization during the 2030s, 2040s. They're being trialed, piloted. What have you got?
Yep. So indeed, in road D and E, we have those sectors that are, first of all, these are the most energy intensive and carbon intensive industries. We have cement, we have steel, we have aluminum, and we have chemicals. So of course, it's critical for decarbonizing them. It's critical to decarbonize them for meeting our climate goals. The challenges in these sectors are multiple. So we have first of all, is the early stage of the technology readiness that we can use to electrify them. So we have some pilots here and there. For example, for chemical crackers, steam crackers, we have demonstration plants that are currently ongoing and running from BASF in the Verbindung site in Germany. Their goal is to test resistive heating to decarbonize e-cracking and to decarbonize steam cracking, and they aim at decarbonizing the production by 90%. But this is at pilot stage. We also have some testing that are ongoing, for example, in the aluminum industry for calcination. Calcination of alumina runs at 1,000 degrees, more or less. And we have, I think, a pilot test in Australia from Alcoa that are looking at electrifying this process. Then we have for cement calcination, we actually have electrification of calcination is something that is doable. There are several pilots ongoing. There is Leilac who is running different pilots in different sites. And we also have Heidelberg Cement, I think, is going to look into electrification of calcination and electrification of clinker making. Clinker making is the most energy intensive part of cement manufacturing. It runs at very high temperature, over 1400 degrees. So, and I think Heidelberg is looking at electrifying this with plasma torches. Plasma torches, like I said, can reach way above 1400 degrees, and there have been already some pilots with other companies involved. So then we have primary steel. This is probably the most transformative approach to electrify this industry, because what we don't have many options when it comes to direct electrification. We either scale up the production of secondary steel with electric arc furnaces, but this has limitation in the supply chain of scrap. So we do not have enough secondary steel to feed the demand that we need for steel. And there are also some other challenges related to the quality of the material. So we are left with the electrolysis. So this is reduction of iron using the electrolytic cells. We have some pilots ongoing, but as you can imagine, this is a completely different approach to steel production. So it's completely disruptive, so of course challenging.
And that would be companies like Boston Metal and I believe
Exactly.
Fortescue, but I think quite a few of the steel companies have got pilots and technological platforms they're developing.
Exactly. I believe that ArcelorMittal is looking into alkaline electrolysis of iron minerals. And I think, there is also a pilot like in the US. But again, these are, let's say, at piloting stage. So that's why a very early stage of development. And of course, like I said, they are disruptive technology. So we cannot retrofit. It's a completely different approach to the steelmaking that we have done in the past, decades. And so, of course, we cannot underestimate that challenge.
And that makes it challenging because at some point you have to put a few billion on the table. So it works in the lab, it works in the small pilot, and then at some point you have to scale up because you won't get the cost point unless you really go big in these technologies,
exactly.
Right?
There are these in the sectors are challenging because we are talking cement plants produce 10,000 tons of cement per day. So we are not talking about connecting to the grid a couple of kilowatt. We are talking about megawatt. We are talking about huge scale. So there is, of course, first the capital investment issue, right? The large capital investments are needed, and de-risking these investments is very important because otherwise we will not have first movers if the perceived risk of investing in this technology is so high. So we need to make sure that we have the right financial support. Then there is the supply challenge. Of course, where do I get my electricity? Where do I plug my furnace, basically? So that's one. And we should also say that these industries do not have so much flexible load. So flexibility can provide cost savings and revenues by flexing the electrical load. And these industries are challenging because they run continuously in large scale, so it's very hard to have flexible load.
In some ways, these have a load profile that's not the same, but similar to big AI data centers. The difference being that they're making a few % margin in the good years, and they're not owned by companies that are worth $1, $2, or $3 trillion, right? So it does make it challenging. Is there work being done on making those demands, those types of users, flexible so that they can actually produce more when it's windy and sunny and the power prices crash to zero, and then perhaps ramp, if they can't switch off, at least they can ramp back?
Yes, so there are some studies that are assessing and looking at how much basically we can monetize the flexibility in this industry. For example, in cement manufacturing, Maybe we cannot flex the clinker making, but we have huge electrical load when we are grinding and milling the raw materials. And this process is something that can be, of course, stopped and then restarted. And this provides, because it runs electrically, it provides the possibility to flex the load. Electrical furnaces in steel making, they are loaded, melt the metals, and then unloaded. So there is a small margin for flexing that. And then also in aluminum, when we use electrolysis to produce the metal aluminum from alumina, we have electrolytic cells in plot lines, and some of them could be switched off and switched on again. They don't provide huge amount of flexibility, but it can be done, and there could be some revenue from it.
Early in my career, I worked as a consultant in the glass industry. And a glass line, you switch it on, you don't switch it off for 25 years, 15 years, some enormous periods. But funnily enough, the way that the energy system is going, we're being pushed back towards wanting to do things in batches, because then, of course, you can take a holiday when there's a Dunkelflaute, a dark doldrum.
Exactly. So in the end, we are switching from an era where we were relying on constant availability of fossil fuels. We are already in the age of electricity, where electricity is supplied by renewables, variable. So we will have to adapt to this variability, and flexibility enables that. It provides the possibility to monetize this variability, But of course, it might require some changes in the way in the business as usual that we are used to.
Now, we had a big discussion about what does commercial mean and what does pilot mean, because what we're trying to do with the staircase is give a simple heuristic. And there's nothing simple, because you can have one plant in some special situation with a high availability of hydro and very few people living, like Iceland, and something might work there, but it might not work elsewhere, and so on. Now, does that mean it's commercial in some places and so on? So lots of discussions that we had as an author team. But commercial, as we interpreted it, was that it would not need financial support, or if it did, it was modest. It was a carbon price that we could envisage in the real world actually existing, like 50 euros, 80 euros, 100 euros, but not, or the equivalent in dollars, but not 500 or 800 or 1,000 and so on. So that was a rule of thumb. I should also say that this staircase, if my co-authors think that it's done and dusted and they're never going to have to think about it again, it's going to be iterative, just as the hydrogen ladder went through. It's on version 5, and I know I'm long overdue to kind of pull it all together and do a version 6. We will be doing other versions. So if anybody disagrees with where things are, or they say it's not commercial really, or it should be, and so on. Now, this is a long preamble for a conversation about hydrogen electrolysis. And we had a big discussion, though, very vibrant, between the authors about where would hydrogen electrolysis fit? And is it commercial anywhere? We couldn't think of a location where any hydrogen electrolysis would happen without some quite substantial, as in more than €100 per ton of CO2 avoided use case. There are places, however, that electrolysis will work. And I can think of, as an example, where hydrogen is used distributed in the economy. There might be a lab using hydrogen. There might be hydrogen used in a power generator. Not many people know some generators are actually filled with hydrogen because it's a lot cheaper than actually creating a vacuum. So it has lower spinning resistance if you fill it with hydrogen. And by the way, don't let it mix with air. But when you need those use cases of hydrogen out in the economy, right now it's delivered by tube trailer very expensively. And I can imagine a use case of hydrogen in the economy that could be electrolysis locally. There are situations where I could imagine that. Trying not to be ideological, there are use cases. And then the question is, will they commercialize in the 2030s or the 2040s? 2030s, it would be on row D. 2040s, it would be row E. And we had a big discussion and decided to collectively, but with some voices louder than others, that it would be on E. In other words, by 2040s, those niches should be really pretty commercial. I also want to just go fairly rapidly, if I might, through the DEF rows, the 2030s, 40s, and beyond for transportation, because that's the only thing that's remaining. And there are things like on row D, river shipping, short-haul aviation. You know, yes, it's very exciting, but we couldn't in all good conscience put it into row C, which would have been commercial now in some places. It is still living on support, subsidies, or investors who are prepared to make losses for probably a decade before it makes money. You've got coastal shipping. Yes, we do see container ships on short routes that are electrified, but it feels a little bit improbable still in the next few years. But potentially, by the time you get to the 2040s, you will see that being common. And then we also wanted to give a nod to some of the people working on stuff that is clearly a lot further out. So medium haul aviation. There are people who want to do long haul aviation electrically with aircraft that would look very considerably different, a bit more like the solar aeroplane that Bertrand Piccard flew around the world and goes very slowly to New York from London. But those, I think long haul aviation will really, I don't want to say it's science fiction, but I'm not sure though that I can put that even on a row F. But medium haul aviation, blue water shipping, that would be ocean shipping, really big ships electrically, and novel chemical synthesis, which doesn't appear, I think, on the actual staircase version that we've got here, but actually using electricity and via all sorts of, it could be electrolytic approaches to securing the carbon as well as potentially hydrogen, and then making chemicals. Because some chemicals are so high value, even though that's an incredibly expensive process, it might be possible to see some commercial use cases. We've put it in as later, beyond 2040. Prove us wrong, we'll all be enormously happy. So that brings to a close the presentation of the staircase itself. I think we just turn to a discussion, if we have a few more minutes, on how do we think the staircase should be used, could be used, at the end of this exercise, what have we learned, and so on. So I'm going to come back to Adrian. What do you reckon? How could it best help with the work of the Electrification Alliance?
I mean, the main thing here with the staircase is the same as the hydrogen ladder. It's about clarity, right? There's so much misinformation out there and so many competing voices. We really focused on getting something that's easily understandable so that policymakers and business leaders can look at and say, okay, this is where I need to focus right now, right? Right now, if someone's telling me that we're going to be using hydrogen in home heating or hydrogen in cars, I know they're absolutely full of it. I can ignore that and I can focus on developing the policy to make sure that this stuff actually happens. So that's a really, really big part of it for me anyway here in Brussels, because I'm dealing with policymakers. That's the big goal, is just to give them the clarity that we can offer, and then acknowledge where we're not sure. That's okay. This is so big that we need to break it down into step-by-step kind of things and say, okay, here we go with the home heating with rows A, B, and C. And we need to, by the way, look at the energy intensive stuff, and we need to put a parallel process in place so that they're ready to jump on this electrification when we get to that stage.
And presumably that policy should acknowledge what is commercial should therefore need removal of barriers versus what isn't quite. And then appropriate policy instruments where it looks more like R&D or big pilots.
Yeah, absolutely. I mean, what it's going to take to really roll out, make sure all of our domestic heating is electrified, is that all the different levels of government get that into their head and they can remove those barriers, right? We've got so many local planning permission problems with heat pumps and things like that. I think these are needless barriers to electrification. So let's focus on getting rid of that.
Tom, useful exercise, learnings, because you have done work over the years in quite a few of these different use cases, not just the ones that I asked you to speak about on the heat on rows A, B, C and so on. Has this been already useful in your work?
Looking at these lower stairs, so these ABCs, this is really giving some focus to say, look, these are great opportunities to improve energy security in industry, to decarbonize industry at very little cost. We're saying it's very cost competitive. It only requires a small amount of policy support. It's really thinking what's going to give us good value for money. Like what can we support right now that has a legacy, so it stands on its own feet and doesn't require too much money. It's also important when we think about infrastructure and grid planning. It's important that system operators, when they're planning grid rollout, know what kind of loads to expect. So what might be connecting. So they might be aware that there's industrial sites situated or already connected to their networks. And this is a really useful tool for them to start thinking, okay, we've got sites of this specific type. We can see that that's a likely future new electric load. Let's start engaging with them now and let's start planning adequately.
William, this is a simple heuristic. It's probably 40 different use cases and 6 levels, and it's all very simple. There's another way of doing this, which is by trawling through, I think is it 3 billion kilometers of route data just on one use case of regional trucking. What is your observation? Because you've seen the simple heuristic and the detailed, AI-driven analytics. What can we use this tool for that we can't do via the detailed analysis?
I think this tool is a way of providing a very simple way of telling you exactly where to focus first. So rows A to C, the focus is about commercialization and about bringing scale, whereas above that, the focus is more on innovation. And I should say, if you look at the 3 billion kilometers of truck data and simplify it, you'll get to a very similar picture to what we have here, because there's a certain set of rules around driver brakes and just the typical distances between stops of loading and unloading that mean that if you look at the really detailed data, it will sort of tell you where to put the infrastructure, but the overall picture is as we set out there.
That's right, and I think it's really important to get that nuance, to communicate, to be able to kind of surf from. Because at the one end, you've got electrify everything, which is nonsense, or electrify almost everything, which is correct, but it's still not that useful for a policymaker. And they might feel very comfortable that they're working on the right thing, but they do need a level of nuance around what to work on first, what to expect when, what is R&D versus what is rollout.
What the staircase really clearly shows, again, for transport, as I said earlier, 80% of the emissions on rows A to C. So what we have in transport is a big problem that's relatively straightforward to solve, and then at the top, a small problem that's very difficult to solve. Well, which of those two things should you focus on as a policymaker? Clearly, doing the stuff that's the bulk of the emissions and that you can accelerate today.
Adding to that, I think it's really important to say that dealing with the easy stuff makes the harder stuff easier later on, right? Bringing on the heat pumps in the EVs gives you that flexible demand, which will bring on additional renewables, which will lower the price for everyone. And Michael, your point always about it's a network, right? We lower those costs for everyone. And then the more energy intensive ones get much, much easier to tackle.
That's right. The point I'm making often these days is that the key to getting electricity prices down is actually electrification. When we made more phone calls, we got cheaper phone calls. And a network that has got network costs, transmission, distribution, batteries, synchronous condensers, all of those costs, volume is key to pushing down the prices. Sylvia, when you wrote your first paper, as you explained earlier, you started with the question of, are there commercial technologies? Are there mature, you said mature technologies. I don't think you used the word commercial. This has brought in a dimension of economic competitiveness within plus or minus an acceptable carbon price. But it's also brought in a time dimension. So do you feel that this has been a useful point on the sort of arc of your have you learned from the process? And when you talk to clients or you talk to policymakers, do you think that this tool is going to help you to kind of move them along towards where you need them to be?
Yes, absolutely, Michael. And for me, it's been an interesting journey in the last 6 years to observe what has happened in the electrification landscape, especially for industry. But there are, of course, now I think we are at the stage where we need to make a step forward. And if we want this raw D&E to be, or the sectors or the applications that are now in raw D&E, if we want them to be in raw C and B, we need to take some action. And I want to divide these actions into something that we can do and something the policymakers can help us with. So what we can do is, first of all, disclose real economics. So today, if you read a report on electrification, we see a graph with a levelized cost of it, comparing heat pumps, boilers, gas boilers, electric boilers. We cannot electrify heavy industries only with heat pumps and boilers. We need other technologies, and we need to understand the economics of these technologies. So this data, we need data that can tell us how much will it cost. The second thing, always on the cost analysis, is we cannot rely only on CapEx and OpEx analysis. We need more. Because electrification is not just a procurement strategy, it's a resilience strategy. When we need to understand the added value, we need to include these assessments into our financial planning. So if I electrify, I'm shielding myself maybe from geopolitical shocks, volatility of fuel prices. I'm preventing myself to expose my company to transition risks, to potential carbon prices, I get access to funds. For example, right now there is the Industry Decarbonization Bank, and the European Union is putting aside some fundings and grants and money, so we can access that. So the idea is, what is the added value that I get from electrification beyond only CapEx and OpEx? And then there are the challenges that are technical. So like I said earlier, we can electrify cement with plasma torches in terms of temperature. So if it was so easy, why we are not doing it at the scale that we need to do it? There are other technical challenges, and we need to discuss them, like we did for heat pumps. So, for example, the scale is one. We are used to apply certain specific electric technologies, like plasma torches, at very small scales or niche applications. So we don't do it at the scale that we need for cement manufacturing. And this is a real challenge. So to really be able to demonstrate that this can be done at large scale.
I want to draw things to a close there, only in the interest of time, but what I would say is everywhere that I go in the world, people are talking now about electrification in a different way. We've got here in Brussels an electrification plan that is being worked on. In Australia, there are teams working on getting electrification into the COP process via Australia's role in Antalya COP31, preparing the agenda there. I've just been in Canada, conversation about electrification. In the UK, conversation about electrification. So it is the topic. It is no longer blocked by the speed bump of hydrogen. And I think it's moving at an enormous speed. So what my hope is that the electrification staircase will contribute to those conversations around the world about electrification. I should also mention, of course, China, which is leading. We haven't talked about China's role, but it is out there. The sense that I get is that they understood all of this quite some time ago and have built the supply chains accordingly. So I would like to thank our panelists here today. So we have Adrian Heel, the Electrification Alliance, Sylvia Mededu, Schneider Electric, one of our Leadership Circle members. We've got Tom Butler, Regulatory Assistance Project, and Will Drake of Liebreich Associates and Ecopragma Capital, also, by the way, one of our, coincidentally, one of our Leadership Circle members. So we will put links in the show notes to the electrification staircase and some background material. And with that, I would like to thank our producer, Oscar Boyd, our video editor, that is Jamie Oliver, our head of operations, Kendall Smith, who's organized the event at which this was recorded and also been coordinating all of the activities around this panel. All of our Leadership Circle members who support what we do here, the recording of these episodes, but also the events that underlie them. And of course, you, the audience, for spending some time either here in the room in Brussels with us today, or via the podcast platforms that this can be reached on, or on YouTube. And with that, let me say goodbye, and please join us this time next week for another episode of Cleaning Up. Cleaning Up is proud to be supported by its Leadership Circle. The members are Actis, Alcazar Energy, Arup, Copenhagen Infrastructure Partners, Signum Capital, Davidson Kempner, Ecopragma Capital, EDP, Euroelectric, the Gilardini Foundation, KKR, Mitsubishi Heavy Industries, National Grid, Octopus Energy, Quadrature Climate Foundation, Schneider Electric, SDCL, and Wärtsilä. For more information on the Leadership Circle, please visit cleaningup.live. If you're enjoying this episode, please hit like, leave a comment, and also recommend it to friends, family, colleagues, and absolutely everyone. To browse our archive of around 250 past episodes and to subscribe to our free newsletter, visit cleaningup.live.